Okay, and then the third step is that you have to um, estimate the Holt exponential smoothing model with this package forecast. And then the next step is that you have to evaluate the forecasting from by using this model. You have to evaluate that one. And this is another method of evaluation, root mean square errors. And then at the end, we have to check it. How can we test the data is stationary or not stationary? Okay, and you know that if you want to use the ARIMA model, you have to test that the data is stationary or not stationary. If data is not stationary, then might be you will implement a first order difference, second order difference. So wherever you find out, okay, no, the data is stationary, then you use that data set into a ARIMA model. Okay. So okay, now let's do these things. So first of all, uh, have you saved your files in a folder from Athena? Okay. And if you save the files like these files, if you save this file in a documents, then you don't need to set any working folder. Okay, if you save this file in a my documents folder. If this file is not available in your documents folder, then I will say that, okay, you export this file by using this option, this graphical interface option, this one. Okay. And then here you can browse this file. My file is available in this folder. So wherever your file is available. Okay. And then open it. And this file is available here. And then I can import it. And now this file is imported in the R. Okay. So it's up to you. Okay. For me, because I'm working in the Windows, so I I save my file in this folder, and my R file is also available in this folder. And when I open this R file, so you will see that my this the folder become my working folder automatically. Okay, if I open the R file from the folder where I have a R, where I have the data sets, then this folder will become automatically a working folder. Okay. Uh, but you don't need to worry about that one. Wherever the file is available, you can just use this option. Okay, from text, browse and look wherever the file is available. Might be in C drive, V drive, wherever you save it. Okay, and then you just select this file and open it and import. Okay, and now the data is imported in the R. Okay, so I can view this data set. Have you done this part? First, download the dataset from Athena and save it wherever you want. Okay. And then use this option and import the dataset from text.
One question. What's the difference between the
Here there are, this one is special for the CSV. And here there are other lot of text files, you can read it. So now I'm start, because now I open my R file. So I showed you here are two procedures. One, use import the datasets by using this option, or either you just directly run this command if your R file is in the working folder. Okay. And then you will see that I can view this dataset here. Okay. Okay, the next task is that if you look your data set, here I have two values for the month 9. Okay, so I have to delete one here. So it's a monthly data set, but for 2021, for month 9, I have a 2 values here. So, okay, then it's mean I have to delete this last row. So in order to do this one, I will write the file name, okay? And in the square brackets, before the comma is for the row index, and after the comma is for the column index. So I have to delete the 61 row, okay? And then you have to write it a minus sign. So it will delete a 61th row from this file, and then I will save it in the same name, okay? And if you run this one, and now if you look this one, 61th row is deleted from the file, okay? Have you done this part? So we have a
Thing on my workstation. And there's the data as well, that it didn't look the same.
you are using the same data set that I am using. Okay.
I thought when I was getting the same in that. Also.
Yes. Why will you say it is not in files from this file? So I just yes, it's okay. Okay, now it's depending upon us. Yes. This is the okay, now the next two commands is important. Sometimes you have maybe a very big data set, and then maybe I want to look at maybe a first few lines of my data sets and the last few lines of my data sets. Okay. So then I will use this head commands and the name of the file, and you will see that I can just view a first 6 rows of my file. And then if you write a tail and run it, and then you can view a last 6 rows of the file. Why this one is important? Might be you have 10,000 values, and then if you want to look it directly from, if you click there and directly looks the last 6 value, it is not a viewable. Okay, you cannot view that file numbers. Then it's important you use this file tail command. Okay. Okay, now this data set contains date, um, the opening price of index, highest price, lowest price, close price, and the adjusted close price, and the volume. Okay, might be if you want to remove it, because here I will work with the close price. Okay, so maybe this high and the low price is not important for me, these two columns. Okay, and then before I deleted the 61th row, and now I want to just delete this column and this column. So it's column number 3 and the 4th. Okay, so then again I will write the name of the file. Okay, in the square brackets before the comma, you know that it's for the row index. So I don't need to do anything with the row index. This time I have to delete with the columns. So here I will write a vectors where I indicates which columns I want to delete it. So here I want to delete it column number 3 and the 4. And then this minus means I want to delete that column, 2 columns. And then I will save the file in the same names. Okay. Now if I will do this one, okay, again if I run the commands, and now you will see that I don't have these 2 columns, low and high stock prices. Okay. Okay, next, in this file, I create a one new variable. Okay. Why am I want to create a new variable? If you look here, we have to do this task. Log returns we have to find out. And if you look the formula of the log returns, it's a log at the current time, log prices at the current time, and here the log prices at the previous time. Okay, so it's mean if I have the log of prices, then I can do this step. Okay, so first I need a log of prices. Okay, so it's mean in my file I have to create a one additional column with the log of prices. Okay, so how can I create that one? So my file name is this one. In order to create a new variable that contains the log of prices, so here I write the dollar signs, and here you can write the names, whatever the name you want to give it, the new column. And then here I will take the log of this column, and you know that how can we access this column from this file. So first I will write the name of the file, and then the dollar sign, and then the name of the variable. Okay, and then I can access this only this column. Okay, you can see that if I just run this highlighted one, I just extract this column from the whole file. Okay, so I have to use this column and take the log. Okay, and save it in this new variable that I created in the file. Okay, if I run this one, and if I don't look again my data sets, no data sets contain a new variable, this one that I created with this command, and I save the log of close prices in this column. Okay, have you got this one? Okay, so now I have this log of prices, and now by using this formula I can get the log returns. Okay, so I have to take the log prices at the current times and and then minus log prices at the previous time. Okay, so how can we do it in the R? You just have to write it the difference of this column, log of prices. Okay, and then it will automatically take a first order difference. Okay, this diff command. And one thing more, here I create, here I have write a 0. Why I'm writing a 0? Because if let's say if I create a here, maybe I will open this one. Let's say here I create a the column for the difference between these two values. So you know that if you take the difference for the first row, because there is no previous value, then we have a 0 there. Okay, for the first row. But for the second row, when I create a value here, so I can get this value minus this value, I can get the value. Okay, But for the first row, I don't have any value. Okay, if I take the first order difference. So it's mean if I just use this diff command, so it contain one less row compared to, I have a 59 rows, but if I just use a first order difference, so it will give me a 58 rows. Okay, so then in this way I cannot join this column with my file because it's contain a one less row. Okay, so in order to join these things with the file, so here I create a, okay, let's say I say, okay, in the first row I have a 0. Okay, so I add 0 in the first order difference column values. Okay, and then I have a 59 values. Okay, and then here I create this one is a log returns, and I create a column in this file. And then if you run this one, and now if you look this one, here is the log returns. Okay, and here is the first is 0. I wrote by myself is 0 because when you take the first order difference in the first row, you don't have anything. Okay, and then in that sense, you cannot join your column with the file. Okay, in order to join the column with the files, the column length should be the same as the column length in the files. Okay, so that's why I create a 0 in the, yes, and then it will not join it. It will give you the error. It will give you the error. Okay, because if you just join the diff, then it contains a 58 values, and my file contain a 59 values, so it will not join. Okay, so that's why I create a 0 before. Okay, now we have done this part. Okay, just using this diff command, we got this log of returns. Okay, then the next task is that we have to divide our data sets into a test and the training data set. Okay, so maybe I will take a last 4 values as a testing data set, and before the maybe it's 50, okay, 50, 55 I will take as a training data set, and last 4 value I will take as a test data set. Okay, so by using the 55 values, I will fit the model. Okay, and then predict it for the last 4 value. Okay, and then we already know that the last 4 value I missed it because that one is the testing one, and then we look at how much the difference between the observed testing value and the predicted values from the model. Okay, and then we can check the forecasting ability of the model. Okay, okay, let me do this one and then I will show it to you. So first of all, okay, one thing more before going to this training and the testing data set. Where is the, okay. So because here the first have a 0 values, so I don't need this first row. Okay, because I'm not working with this 0 values. Okay, my difference values is started from the rows 2. So might be I will then delete a row 1 also. Okay, so in order to do this one, here you will see that I will delete the first row. Okay, so I will write the name of the file. First index is for the row, and then I delete the first row. Okay, and now so now I have 59 values. Okay, why I deleted the first row? Because first row contain a 0. So I will not work with that row. Okay. Okay, then before dividing my data sets into a training and the test data sets, so might be we have to create a time series plot. Okay. In order to create a time series plot, okay, now I have to create a time series plot by using the close prices. Okay. So let's say first I will show you, if I just run this one and I just want to look the variable close, and you will see that it's just numeric values 59. Okay. But I convert this variable into a time series variable. Okay. How can I convert this one? If you write a TS time series and then this variable, and this variable value started from 2016, because if you look here, the data set is start from 2016. Okay. And then it start from 11 month. If you look at here, it start from 11 month. And how many frequencies I have in the years? I have the 12 frequencies because I'm using the monthly data sets. And then I will save this data set as in the file. And now when I access this variable, it will be converted to a time series variable. Before that, it was like this. It's just the numeric variables. And after converting into a time series, now I have the values with respect to time. Okay. So this is the 2026 value in November. Okay. Then I have values with the time. Okay. Similarly, you can convert this log of returns into a time series data set and use the same command TS and the starting values 2016, 11 month, and how many frequencies, because we are using the monthly data, we have a 12 frequencies. And now I can convert also, this one is in a time series data set. Okay. So once I convert these two variable into a time series data sets, then I can make a time series plot. Okay. And then you have to use this TS dot plot. And then first I will plot the close prices, and then I will plot the log of returns. So I will use this TS plot, which variable I want to plot it. And then main is the heading of the plots, and Y label is used for the labels for the Y axis. And if you run this one is the time series plot, and you will see that here the time is available. Okay. So if you make the plots without time series, then in the x-axis, the time is not available. Okay. So is this data stationary or not? No, it has a trend. Okay. Okay, now I will plot the log of returns. So I will do the same, but I did it when I plotted for the close prices. So now log of returns are stationary or not? Approximately. Yes, it's round about here, around about on these values. Okay. So maybe I can draw horizontal values by using this AB line. Around 0, I want to draw lines horizontal. So it's around this red line. It's randomly around this red line. So it's a stationary data set, so I can say. Okay, then the next task is that we have to split the data set into a training data set and a testing data set. Okay. So in this case, I will use last 4 values as a testing values or the testing data set, and the 55 values as a training data set. Okay. So first I will use this, I will create a test data set by using the last 4 values of the data sets. So here, write the name again in the square brackets before the comma is for the column index. So here I have written that I will take a values from 56 to 59. Okay. So here n rows of the name of the file mean how many rows I have it in the file, and then -3 I will get a 56, and then this column it will take a difference from the one by one, and then n rows is the total number of rows. Okay. So it's mean by using this 56, 57, 58, 59 values, I will save it as a test data set. Okay. So now I will run this command, and this one is my test data set, and it contains the last 4 values for the close prices. Okay. And now I have to create the training data sets. Okay. So for the training data sets, I need the values from 1 to 55. Okay. So again, I have to write the file name, and in the row index, I have to mention it start from 1 to 55. Okay. So it start from 1, and either in this place you write it 55 if you know what is the last value. Okay. Or either I can write how many values I have in my file -4, and then it's a 55. Okay. But anyhow, if I just run this one, you will see that I will get index from 1 to 55. Okay. So if I run this whole one, then it will save 1 to 55 values in a training data set. So I have this one in a training data set. So I have a 55 values. It's not a 56, okay? Because it start from 2. So that's why in the index it's a 56. Okay, but it's actually we have the 55 values in the data set. Okay, now we have done this second steps. We divide the data set into a testing and the training data set. Okay. Yes. I will let you know. Okay. Now we have to use this 55 values. After this one, you ask this question. Okay. Now I will use this 55 values, and then I will fit this Holt exponential smoothing model. Okay. So based on this 55 values, I will fit this model. Okay. So first I will fit this model here. So in order to you estimate the model, that is a Holt exponential smoothing model. So first I need to install this package, this forecast. So it's up to you. Either you go on the package here and then install and write a forecast. Okay, and then install it. Or either you just run this one, install that package and the name of the package. So I will run this one. So now the package is installed, and if you want to confirm it, either the package is installed or not. So here the forecast package is available. So it's mean the package is installed. Okay. So once the package is installed, I have to attach that package into R. Okay. So how can you attach that package? Then you can use this library command, and you run this one, and now the package is attached with R. Okay. So whatever's the functions available in that package, I can now use it. Okay. Once I attach the package with R. Okay. Okay. No, because this Holt commands is available in this package. So I already attached this package. Now I can use this Holt commands. Okay. So I have to fit the model, this Holt exponential smoothing model, by using the close prices that is available in the training data set. Okay. And here I will say that, okay, after fitting this model, I have to forecast 4 values. Okay. Because last 4 values, I take it as a testing data sets. Okay. So here I will say, okay, predict by after fitting this model, predict for forecast values for 4 years, next 4 years. Okay, then here I have written exponential is false. Okay, maybe you can write is a true. Might be if it will work on the data sets, you can use that one. Okay, but I will use it here a false. Okay, once you run this model, you have to save it in some object. So I will save it with this name. Yes. Yes. You can choose 6. It's just up to me how many values I can choose it. If you have 1000 data, maybe you can say, okay, 80% data I can use it for the training purpose, and 20% data I can use it for the testing purpose. Okay, so usually if you have a very big data set, usually we divide the data set into 80% as a training and 20% as testing. Okay, but here I just randomly choose 4 values. Okay. First, I will fit the model by using the 55 observation. Once I get the estimate from the model, and then by using that model, I will predict for the 4 years. 56 to 50. Yes. Yes, it's correct. But it's correct, you did it because index start from 2. Yes, I use that one as a testing. Just let me finish this one and then ask me this question. Okay. Should I start now? Okay, now I will fit this model and save the result in this variable. Okay. And now if you want to get the detailed results from this model, you have to write a summary and then the name of the variable where you save the results. So here is the alpha and beta, that is the smoothing parameters. Okay. Maybe I will show you, you have in the formula sheet. So we estimate this model, Holt's model, okay? And then you need alpha and beta here, okay? So these alpha and betas, we have it here, okay? And once you get this alpha and beta by using this equation, that level estimate and the trend estimate, you can do the forecasting by using this equation, okay? And then you need some starting values. And this is the starting values for the level estimate and for the trend, okay? And then you have a AIC value, AICC value, and the BIC values, okay? Here, I will not say anything about this one, but if you have the 2 models, and then you have the AIC values for the 2 models, then you can compare it, which model is the best one, okay? So then you have to check it, which model have the lowest value of AIC. That model will be the best one, okay? Because here I don't have any other model for the comparison, so I cannot say anything about this one, okay? Similarly, this one is the model goodness of fit criteria. So I expect that the mean errors, root mean square errors, they should be less, okay? And then here is the forecasting values. I use a 55 values in order to estimate the model. And then based on the model, I forecast these 4 values here. Okay. So now I have the forecasted values here, 4. Okay. And now if you plot this model, so this one is up to this point, the data set was available. And based on the model, these 4 values I forecasted. Okay. And then this dark gray colors, it indicates the 80% confidence interval and 95% confidence interval. Okay. So the dark gray color is for the 80% confidence interval for the prediction or the forecasting. And the light gray color is about the 95% confidence interval. Okay. And let's say no, I have in the testing data set my actual values, because here these dot represent the forecasting values from the model. Okay. But in the testing data set, I already know the actual 4 values. Okay. So maybe I will plot that actual 4 values. So these was the actual 4 values that I missed it from the model. And these colors values are about the forecasting values. Okay. So if the forecasting values and the testing values, they are close to each other, then I will say that my model is a good one. Okay. So that's why I skip last 4 values. Okay. In order to check the model predictable forecasting ability. Okay. So that's why I missed it there. So, okay, now here you can look graphically how much they are close. Okay. Might be here it's not too much clear. Why not I start the graph from 0 to 60? Why not I just start from 50 and then I can easily visualize it, how much difference is between the forecasting values and the testing values. So, okay, now, yeah. So now here I will start it. I will start the graph from values number 50 to 60. Okay. So I cut the graph. I skip the first 60 value. No, 50 values. Okay. And then here you will see that this one is the forecasting one. And these 4 was the actual values. That was the testing one. Okay. So you can easily visualize it, how much they are close or not. Okay. But instead of saying graphically, definitely we will use some numerical formulas to evaluate it. Either these values are close or not close. Okay. So which formula we will use it? Then we can use these formulas in order to check the forecasting ability of the model. Okay. So if the mean errors are lowest for the model, then the model is a good one. Okay. So might be you can check it mean square errors, root mean square errors, mean absolute deviations, mean percentage errors. So you can use all these formulas. Okay. Okay. Now, here I save the result of this model into this object. So from this object, I have to find out first the forecasting values. So the forecasting value, you can access it if you write the name of the models objects where you save the result and $ mean. So this will give you the forecasting value. So if I run this one, and you will see that I got this forecasting values, and these are the values there, this one. Okay. So now I just extract these 4 values from there. Okay, next is that what are the testing values? So here I got the testing values. So these are the testing values and these are the forecasting values. Okay. Once I have these 2 values, and then I have to check it by using these formulas, how they are close and how they are away from each other. Okay. Okay. To implement these formulas, you know that here I need the actual values and then the estimated values difference. Okay, I need error terms here. Okay, So here I have the actual values, and here I have the forecasting values from the model. I take the difference from the between them, and I will save it with this name. And then by using this forecasting value, actual values, and the error terms, I will create a data frames in the in R. So I will combine all these variables, and then I create a data frame. Okay. So these was the actual values, and these was the forecasting values from the model. And here is the error. If I take the difference between these two values, I will get this one. Okay. So I need this last column in order to find out this mean errors, means scare errors, root mean scare errors. So how can you get this, implement this formula in AR? Now you have to do these things by yourself. So I create this file that have this one, actual minus the estimated one. Okay. And you need that one in order to get this mean errors, mean scare errors, root mean scare errors. So how can you implement it into R? Okay, maybe I will just implement this one. Okay, but the other formulas then you will do by yourself. Okay, now I have this file, and this file contain this error terms. Okay, so if I want to get first, so I extract the errors and save it as a E. Okay, and then you just have to take the mean of, so now you will get the mean errors. Okay, so from the file I just extract the error terms and just take the mean of that one. And if you look here the formula, so this part is your error terms, and then you just take the mean of that one and you will get the answer for the mean errors. Okay, and let's say if you implement this one, then you need a scare of error terms, and then you have to take the mean of that one. So if you just take a mean, so this is the mean scare errors. Okay, so if you take the square root of these values, you will get the root mean square errors. Have you done this part? Because before we just graphically look how the forecasting values and the testing values is close to each other. Okay, but anyhow we need some quantitative values. Okay, oh, this forecasting is a good one or not. Okay, then we can judge it by using these formulas. So we need a smallest values for this, for all these criteria. Okay, so because I just fit here a one model, so maybe you have some other models, and then if you want to compare two models, you can compare this mean errors. Which models have the less mean errors, that model is a good one. Okay, which model has the less root mean square errors, that model is a good one. Okay, and then you just take the square root of these values and this value, then you will get the root mean square errors. Okay. And then the next task is that if the data is available and we have to check the data is stationary or not stationary. Okay. So so then we will use this Dickey Fuller test. Okay. And this mean the data is stationary, and this mean the data is not stationary. Okay. And okay, to check the stationarity of the data sets, I will use this package. Okay, so you first need to install that package. So I will use this command, or either you go on the package menu and then write the package name and install it. Okay, it's up to you. So I will run this one. So I install this package. So now if you want to test this one, so you will see that this package is available here. Okay, but yet it's not attached with R. Okay. So first I have to attach this model, package with the R. So I will use this library command. So now this package will be attached with the R. So here you will get this activation of this checkbox. Okay. Here. It has some problems if you have the newer version of R and the older version of R, the newer version of package, but it will work. Like here I have the same problem, but it doesn't matter. Okay, now you have from this package, you have to use this adf.test. Okay, and which variable you want to test it's about the stationarity, you just have to give that variable. Okay, but this function will implement a augmented Dickey Fuller test. Okay, it's not a simple Dickey Fuller test, a regular Dickey Fuller test. Okay, because this Dickey Fuller test, it will choose automatically how many lags we have to use it in order to test the stationarity. Okay, but in the formula sheets, we only use a first lag. Okay, so this one is this test is about the regular one. Okay, non-augmented one. Okay, so first I will check it with the augmented one. So here you will see that it's automatically takes the three lags and test the stationarity. Alternative hypothesis is that the data is stationary, and because we have the high p-value, so we do not reject H naught. So it's mean the data is not stationary, and we know that the data has the trend upward. Okay, because I use the closed data set, and from the graph we know that it has the upward trend. So there is no stationarity here. Okay, so testing of hypothesis say the same things. Okay, now I will implement this one that is available in the formula sheet. So it only can, for this test, it's only takes the first lags. Okay. So then in that case, I have to mention it, how many lags this test will use. So then I will say, okay, k is equal to 1, only use the first lag. Okay. And now I will get the results, and here you will see that I'm using only the first lags. And now we got the same results because we got a high p-value. So it's mean we do not reject H naught, and H naught was data was not stationary. Okay, and you here in the output it's written the alternative is that the data is stationary, and the null hypothesis is that the data is not stationary. Okay,